Okay, so now that we've discussed what an average rate of change means, and then also the formula for finding it, you're going to get some pretty straightforward questions that look like this on your homework here. To find the average rate of change of a function that was given to you here of f of x equals x to the 1/2 power, and on a particular interval here from 0 to 9. So let's not overthink this one. We learned a formula for average rate of change, and this is just the notation that I tend to use for that quite a bit, and it was f of b minus f of a all over b minus a. So knowing what the function is, f of x is x to the 1/2, and knowing our a value and our b value here, this shouldn't be too tough to find out. Okay, so average rate of change equals, and here we go. F of b, we're going to find that by plugging 9 into this function right here. And of course, you guys, x to the 1/2 is going to be the square root of x. So f of b is going to get us 3 here, minus f of a. Plugging a 0 into that function gets us 0. And then down on the bottom, the change in the x values, that's going to be a 9 minus 0. So nothing too complicated here, guys. The 3 minus 0 on top gets us 3, 9 minus 0 gets us 9, and we end up with 1/3 now for the average rate of change of this function on that interval. Now, if they just gave you a function and not any context for it here and no units, there's not going to be any units for your answer here at all. So, hey, guess what, guys? We're done. Now, if we wanted to explore what was going on graphically, we might take the time, and I think I'll do this with you here. Let me go to a calculator right here. I don't like where I have that, so give me just a second there, everybody. All right, let's do that, make that a little bit easier to read. All right, I'm going to go home. I'm going to start a new document. No, I don't want to do my changes, or save my changes, so we'll just go something new. And let's go ahead and graph this one out and see what happens. So the function we were graphing was x to the 1/2 power, so x to the 1 over 2 power, and that's the square root of x function. Hopefully that doesn't surprise you at all. And the 2 points we were talking about were when x was 0 and where x was 9. So to plot those, everybody, I'm going to go to Menu. I'm going to hit number 5 for trace and number 1 for graph trace. And right now, it always just starts at x equals 0. I'm going to hit Enter, and that's going to plot that point permanently. Now, instead of just hitting my right arrow a bunch of times, I'm just going to type in 9 and hit Enter, and that moves my cursor over to the point 9, 3, and I'll go ahead and hit Enter, and it labeled that point there also. I'm going to hit Escape now, everybody, to get out of the trace, and now we're just looking at the graph a little bit better. And what we think we have found, everybody, is that the average rate of change of this function on the interval expressed here from 0 to 9, we think was 1/3. Now, if we think back to what we talked about just a moment ago, the average rate of change is defined by using 2 points on a curve, and a line defined by 2 points on a curve is a secant line. So I'm going to go ahead and graph that, everybody, and let's see how this looks. I'm going to do this a little bit backwards, but I'm going to hit Tab right here, and I'm going to now type in what I believe to be the equation of the secant line that passes through those 2 points. So what do I need for equation of a line? Well, I need the slope, which we think we just found was our average rate of change. So I'm going to type in 1/3, close that off, multiply that by x, and I would add my y-intercept to that. But since this is passing through the origin 0, 0, our y-intercept is just 0. And when I hit Enter, I believe that that's going to give us the one and only line that passes through both of these 2 points. Let's see how we did. And there it is, guys. So what we just graphed in red right there was the secant line, the one and only secant line to this particular curve defined by those 2 points. So what does that mean for us? It means that on average, this function has a rate of change of 1/3 on this interval. And if we think about 1/3 as a slope, change in y over change in x, what that tells us, guys, is that for every 3 units of increase moving off to the right, you go 1 unit up. Now, if we think about that on the blue curve, everybody, if I were to try to trace this out right here, from the origin, if I went 3 to the right and 1 unit up, I'm below the blue curve right there, which means the blue curve is actually increasing at a rate faster than 1/3 for the first 3 units of change on the x-coordinate. But then as we start to move further to the right, to 4 to 5 to 6 and then up 2, it gets closer. and then it eventually matches over there at the 0.93. So the rate of change of the blue curve isn't always 1/3, but that's just our average then on that overall interval. Those are pretty straightforward problems, so I don't think you guys are going to have any difficulty with either the worksheet that I had asked you to work on from 2.1, or there are some book problems that deal with that as well. That should be pretty easy. Wanted to give you one other one, not because it's difficult. This one just throws a little bit of a wrinkle at you now. So again, we are finding an average rate of change of a function now g of x being a trigonometric function on an interval here from pi over 3 to 11 pi over 3. Okay, so change in y, or change in g, everybody, is going to be the cosine of 11 pi over 3 minus the cosine at your a value, which is negative pi over 3, all over the change in your x values now. So 11 pi over 3 minus a negative pi over 3. And let's see what happens with this one. I kind of wanted to talk about it because I think some of us may still need a little bit of brushing up on our basic trig values, on the sweet 16 values on the unit circle, and I know it's something that doesn't get brought up a whole lot. So we're just going to freehand this one, everybody. So x-axis, y-axis, and here's our unit circle. And let's see where we should be looking here. 11 pi over 3. All right, pardon me if I'm patronizing you guys just a little bit right here, but if you're not quite sure where 11 pi over 3 is, what I'm hoping you guys notice is that your denominators for all of these angles are 3. And pi over 3, I'm hoping, is one you guys have memorized. That's a 60-degree angle. So what this means is I'm going to start, as we always start, right over here, straight to the right, east, 3 o'clock, and that's at 0 radians, everybody. And I'm now going to proceed around this circle in a clockwise manner, taking steps that are a size of pi over 3 radians, or 60 degrees. And if I want to get to 11 pi over 3, I've got to take 11 of those 60-degree steps. So let's get started, guys. Counting by 60 degrees, there's 1 pi over 3. That's one step. 2, 3, 4, 5, roughly sure, and here's 6. Now, if you think about that, this is 6 pi over 3, which if you visualize that, of course, it simplifies to 2 pi, which is right back where we should be. So this was 6 pi over 3. Now we're hitting the same spots again. 7 pi over 3, 8, 9, 10, and 11 pi over 3 is going to get us to this angle right here. So I'll go ahead and label that as 11 pi over 3 radians. From that spot, I like to go ahead and make my triangle, always with an altitude to the x-axis. Hopefully you guys see this already. The reference angle we're dealing with right here is a 60-degree reference angle, which makes this a 30, 60, 90 right triangle. Your x-coordinate then is a positive 1/2. Your y-coordinate is a negative root 3 over 2, and of course your radius is 1. So that's where we are, and to come up with the cosine at that angle, we're always looking at the x-coordinate on a unit circle, everybody. So our x-coordinate right there, after all that work, was 1/2. Minus, now we're going to do something here. We're going to take the cosine of negative pi over 3. And some of you see the joke already. Negative pi over 3, guys. So we start again right here at 0, like we always do, but now we're traveling in the opposite direction, clockwise, because we have a negative angle here, and we're just taking one 60-degree step. That gets us, as luck would have it, right down here to the same spot. And if you forgot this word over the last couple of years, what that means, guys, is that these two angles, because they end in the same position, those are called coterminal angles, meaning that they're not the same angle, but they end in the same spot. They've got all the same values of sine and cosine and tangent. So the cosine of negative pi over 3 is going to be positive 1/2 as well. Now down on the bottom, 11 pi over 3 minus negative pi over 3, that's going to become addition, 12 pi over 3, and that's going to be 4 pi. But that's kind of irrelevant here. As long as our denominator isn't 0, we can see now that with the same number in the numerator twice being subtracted, we're going to end up with an average rate of change of 0. That can absolutely happen. Now, that does not mean, everybody, that the value of your function did not change. Our function was cosine of x, and as you guys know, cosine is always given to you by your x coordinate as you travel around the unit circle. So starting right here at negative pi over 3, and then traveling, let's see guys, 4 pi was our denominator, so we actually traveled around the unit circle a grand total of 2 times. Our x-coordinate changed a ton. It went from 1/2 up to 1, back to 1/2, an x-coordinate of 0, an x-coordinate, let's say, of negative root 2 over 2, an x-coordinate of negative 1, back to negative root 2 over 2, negative 1/2, 0. And it kept going around, but it ended up, that's what's important, at the exact same value at which it started. And so the overall net average rate of change here was 0. If you think about being on a track, everybody, and running a lap, all right, you started in one particular location and you ended in the exact same location, assuming that you did one perfect lap. It doesn't mean that you didn't move at all. You just ran a quarter of a mile or 400 meters or whatever that is, all right? But it does mean that in terms of the overall net movement, you didn't actually change your position overall on average because you ended up at the same place that you started. We'll come back to that idea then in just a second. All right, so those are a couple of average rate of change problems. I don't think those are going to be too difficult for you guys to figure out. All right, but on to this now. Average velocity, everybody, is, and I took the time to write this out right here, average velocity is simply a type of average rate of change. But the significance of that is I don't want you to view average velocity as something different from what we were just talking about. It's really the exact same thing, just with some units involved here. So the formula for average velocity, everybody, is going to be, and let's use a little bit of terminology that's going to come into play here. We're going to use this version of the formula right here. S of B minus S of A, and the denominator is going to stay exactly the same as it was, which is B minus A. Now, when we're talking about velocity problems here, you guys know the units that are usually involved. In your car, you're talking about velocity as miles per hour. Sometimes in physics, we talk about meters per second or things moving of that nature. But what's important here, guys, is that we take this formula right here and we maybe think about it a different way. S of B minus S of A is going to give us the change in the S function, which I'll talk about in just a second. And in this particular context, A and B, which you guys are thinking of as X values, are usually called time values when we're discussing velocity. So this is really going to be delta S over delta T. Now, the important thing to know, and I realize right now that I didn't write this anywhere on the board, and it's kind of important, is that all throughout the year, and not just me, and not just this author, but in every calculus book and in an awful lot of physics books that I've seen as well, S of T, everybody, is the nomenclature that we use most often for finding a position function. I do not have a good answer for you for why we don't use P of T for position as a function of time. But like I said, every calculus book and physics book that I've seen uses S for position. So what we're measuring right here then, everybody, this formula here, is the change in position divided by the change in time. So let's write this down below it, guys. Delta S means change in position, but there's another name for that, everybody, that I want to make sure that you guys understand because it's going to show up a lot. It's the change in position, but make sure you get this word written down, also known as the displacement of your object. So this is one that I need to make sure that you guys know, that delta S is the same thing as change in position, which means displacement. Now I'll tell you guys right now, that word, displacement, will show up in test and quiz questions throughout the year. Displacement means change in position. There's no cool name for delta T, guys, so that is just going to be the change in time. And one more thing before we move on, if you go back once again and think about units, I think this is going to sound familiar to you guys. For average velocity, we're taking a position function in the numerator. So think about what units an object's position might be measured in. Well, position is kind of a small variation on distance, so we could be talking about something like feet. And for change in time, well, you could measure time in a lot of different units, but we might be talking about seconds here. So when we go ahead and do average velocity, your units then are going to end up being something like feet per second. To be a little bit less specific and a little bit more vague about that, you're using a unit of distance on the top and a unit of time on the bottom. And distance divided by time, let's make sure we know this, guys, distance divided by time is the exact definition of velocity. Okay, so there's a formula that I always assumed that you guys had learned in various science classes or math classes up until this point, and last year people really told me, no, Mr. Fontana, we've never seen that before. It would be a variation on this formula right here, and it would be d is equal to RT. Distance is equal to rate times time. And if you notice, guys, if I just took this formula right here and multiplied both sides by t and then changed velocity into rate, you'd get the same formula there. So if this is one you guys are not familiar with, distance equals rate times time, you probably should write that down somewhere, and that would be a good one to have in there. So just mull that over. Okay, so that's a quick talk about average velocity. So let's do a problem with this, everybody. So what we would normally do if we were actually in class, you guys, is to take a look right here and actually do an experiment by dropping an object here. I've done this over the last couple of years, and I'll be honest with you guys, I cheated and I used math and science to come up with this number. My stopwatch skills aren't that precise here, but trust me on this one. It takes approximately 0.612 seconds for an object to hit the ground when dropped from a height of 6 feet. We'll just take that as a given, everybody, and we're going to find the object's average velocity. So again, if we were in class, the little experiment we would have is we would have somebody who's about 6 feet tall come up to, actually, they'd probably hold it up a little bit. We'd have somebody who's about 6 feet tall. Now, that person has one really long arm and one short arm. Now I feel bad. There we go. So that person is going to drop an object from a height of 6 feet. So what's going to happen now is that this object is going to travel 6 feet down, and it is going to take 0.612 seconds for that object then to hit the ground at that moment from a height of 6 feet. And we're going to try to keep this real simple now, guys, and find our average velocity. So average velocity is equal to, we said delta S, which means displacement, over delta t, which means time. And this one isn't that difficult to figure out, although we do need to talk about something important that can get overlooked right here. Okay, delta S means displacement. Displacement means change in position. So the question now is, how far did this thing move during this little experiment? And the answer to that is going to be tempting for you guys to say 6 feet. And it depends on how you word the question, everybody, and that's important. All right, so let's talk about that. What I want you guys to do is remember the concept right here that a secant line, that an average rate of change is the same as the slope of a secant, and that a secant line requires 2 points. We measure this as point A and point B in order to measure the change in between. Likewise, an average rate of change requires 2 data points in order to be able to compute what's going on. So I'm going to start right up here at the start of our experiment, and we're going to call that point A, and then it ends right down here at point B. Now, in this particular problem here, guys, the independent variable, the thing that has nothing to do with the other, is time. So time is really going to be your x-coordinate. And at the moment when you drop the object, your time is going to be 0 seconds. The y-coordinate then is going to be the position of this function, of this item. And be careful now, the position of this item right now is 6. It is 6 feet above the ground at that particular moment. So you might want to note that what we're really doing doing here for this ordered pair is we're talking about time, and then over here we're talking about height or position. So if you wanted to use an H, that would make a lot of sense as well, but that's what's happening here. Now let's talk about point B. We need time, and then we need position at point B. Well, we said that it took 0.612 seconds for this object to fall. So that's the time at which our object is going to be at that location. And the height of that object, its distance above the floor at this point, is 0. Now when we go to find displacement, you always want to get in the habit, guys, of thinking ending minus starting. You can do it the other way, starting minus ending is, no, I take that back. Every time you see displacement, you want to do ending minus starting. And the S means position. So we want to think of this as ending position minus starting position. Really, point B minus point A. So when we go to do this numerator, the ending position, the ending S of this object, it ended right here at a height of 0. Minus now the starting position, which had a height of 6. And that might show you something important. This numerator here, the delta S, the displacement, the distance that this thing moved is actually negative 6 feet. Now we draw a distinction in mathematics. I can't say for certain if they do this in physics or not, guys, because it's been a long time since I've taken that. But we draw a distinction in mathematics between positive movement and negative movement. Positive movement would mean that the object's position is getting greater. Negative movement would tell us, as you'd expect, the opposite, that its position is getting lower. And if you take a look, guys, and remember that this thing went from point A to point B, your height was 6 feet and became 0 feet. You lost 6 feet in position, and that's why this numerator has to be negative 6. Now down on the bottom, delta T. So again, ending minus starting. Ending time minus starting time. Well, the ending time at point B is 0.612 seconds, and the starting time at point A is going to be 0. So that denominator is going to be positive, and that's going to be seconds down there on the bottom. So, ladies and gentlemen, I don't happen to know what this is off the top of my head, I'm sorry to say, so let me add a calculator page and do negative 6 divided by 0.612. Now, because I put a decimal into the calculator, it's going to give us a decimal answer of negative 9.8039 blah, 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 and we always round to 3 decimal places at this level, guys. The sooner we can get into that habit, the better. So negative 9.804 is going to be our answer here. Negative 9.804, and the units are given to you right there. That's going to be feet per second. So that right there, guys, is the average velocity of this object in free fall from a height of 6 feet. Now that's its average velocity. What I think you guys know is that as you drop an object, it doesn't fall with a constant speed. This thing is going pretty slowly right here at the beginning when you first dropped it. But because of the accelerative force of gravity, this thing picks up speed on the way down and is traveling faster at the end. So if we think about what's going on, the object is probably actually traveling slower than 9.804 feet per second here. But at the end, it's probably traveling faster than 9.804 feet per second. So keep that in mind, everybody. Another quick conversation, you'll notice then our average velocity is negative. And that's true for one simple reason, because this thing is moving downward. Its position is getting lower. It's dropping from a height of 6 feet down to a height of 0 feet. It's losing height, and so therefore our velocity is negative, indicating that position is decreasing. If we were going the other route and we were talking about a rocket or a golf ball or something that you hit up in the air, its position is increasing. Now its velocity would have to be positive. Okay, so that's kind of the distinction between those two big ideas there. All right, now you will notice that everything we have done in this section so far dealing with average rates of change, not a one here has involved anything that could be considered a calculus topic. Everything we've done up until this point, you guys have done already. But what we really become interested in calculus, let me go back to that curve that we drew a while ago where we had the square root function, and we found the average rate of change by drawing the secant line between those 2 points. What we really become interested though in calculus is not this concept of an average rate of change, which we know doesn't really give us the full story. It's simply an average, a summary, a snapshot. What we really want to know in calculus is, what is, and here's the phrase of the day here, guys, the instantaneous rate of change of a particular function. We don't want to know what the average velocity of a car driving or an object dropping or a ball in the air is over an interval. We'd really like to know what it is at one particular point, just this one spot right over here. That is incredibly difficult to do because what we really want, you guys don't need to write this down, but let me write this formula again here, that average rate of change was equal to f of b minus f of a all over b minus a. What we really want, guys, is for this interval that starts here at a and ends right here at b, we want that interval to become smaller. We want to move a over here to the right. We want to move b over here to the left. So instead of this big wide interval, we're dealing with a very small interval right here where those numbers are really close. And we can do that. But of course, to be ideal about this, and this requires some mental stretching here, everybody, some squinting of the brain here, all right? If we really want this to be ideal, we don't want to have 2 points. Because no matter how small your interval is, 2 points is always going to give you an average rate of change. But for a true instantaneous rate of change, we don't want 2 x values and 2 y values, we want just 1. What we really want is for A and B to keep going and to actually become the exact same point right here in the middle. We want A and B to be the same number so that there's really only 1 data point rather than 2. Now, if you look at the formula we've written down right here, though, for average rate of change, you can see that that's impossible. If B and A were the same number, your denominator here would be 0. And of course, we can't divide by 0, right, ladies and gentlemen? Right? And that little question right there, can we divide by 0, is actually one of the fundamental ideas behind the development of calculus and what it is that we're actually trying to do here. To answer that question, I didn't mean to leave it as a cliffhanger. No, we can't divide by 0. However, we can sometimes interpret the answer with a little bit of numerical experimentation. So let's go back to this funky little thing that I wrote here, but I haven't talked about at all. Average rate of change approaches or becomes instantaneous rate of change as the quantity, the denominator, b minus a, approaches 0. We can't ever let our denominator equal 0, but we can make our denominator get smaller and smaller and smaller so that we can say it approaches 0. And then sometimes we can take a look at what happens to our average rate of change and infer what the instantaneous rate of change would be as we move on. And that's the big idea right here when we're talking about limits. All right, so ladies and gentlemen, I'm going to wrap it up right here for now. We're going to come back and finish all this up in our next video.